exciting episode of CS101. I'm your host, Scott Manley. Um, yeah, so first off, how was everybody's weekend? Hopefully good. Um, I mean, not that you could really do much over the weekend, but c'est la vie. Um, yeah. All right, well, so oh, yeah, that's probably my fault. This would be, yeah, there we go. Yes, I'm streaming. I just forgot to switch the input. Okay, so now you guys can hear me. Okay, everybody's good. Yeah, we Gucci. Okay. Yeah, sorry. I had it on full screen stream from when I was playing XCOM this weekend, and I forgot to switch it back. So, okay. So let me open up our utility here, or sorry, our notes reference. And what I wanted to kind of do today is, well, let me actually oops, open up um, the assignment file, and then we'll go back to the notes if needed. So what I wanted kind of to do today was to start by asking if you guys had any questions that I could answer on this. The one thing I needed to point out is don't use this last page that's got the quote even better algorithm because there's a bug in it that I need to fix still. Um, and yeah, so don't use this version. Just use this version of it. And then the other thing is that let's see, I could have written this dude right here at the end as an if else or as two if conditionals. If else would have been maybe slightly more efficient because then it only requires two jump or one jump instead of two, but whatever. Um, okay, so yeah, so Mike, I know you have questions. Let me start and see. Do we have questions from anybody whose name is not Mike? Let's start there. Um, all three of us? Wait a minute. Do we only have three people in class? What are you talking about? We've got like nine or ten on the stream chat. Um, so um, yeah, okay. Um, Mike, I'll have to go through your code line by line. I saw that you have posted it, but I haven't looked at it yet. Um, and see what the issue is. Okay, so yeah, but maybe I should rephrase. Let me start with general questions um, on this. Um, Dead Week, gotta love it. Yeah, no kidding. Um, yeah, well, we haven't had the greatest attendance, and based on YouTube, nobody's even viewing the replays. So um, yeah, whatever. All right, so I would I would strongly exhort you, of course, to work on these things in order because they get progressively more difficult. Um, yeah. Yes, and you can also reply on Twitch. There's only three of them in Discord, but you guys can type on the Twitch chat also. So Tyler, do you have any questions? Uh, or Reese? No, not really, Tyler. Okay. Um, All right. Well, let me make sure that it makes sense what we talked about last time, which is that so let me go to the Joel's emulator. Um, First off, this is something that came up in the Discord chat. Uh, you have to have the or sorry, the pound sign at the beginning of your URL. So it's got to have the pound sign, um, uh, and then you'd put your code. So like 1121 or whatever that follows it. But so don't forget the pound sign because otherwise it won't load it correctly. So just FYI there. Okay, so what we were talking about last time was well, a couple things. We talked a little bit more about the rotate command, and in particular that rotating left you can accomplish by rotating right. Um, by the correct amount. But then also the fact that since the program is stored in memory and instructions from the program um, can overwrite memory, you can make a program that self-modifies. Now you want to be very, very careful with doing that because if you modify it too much, then it'll totally screw itself up. But you can totally have a self-modifying program. Which actually brings us, I guess, to a kind of an interesting architectural difference. So, pretty much every architecture nowadays is known as what's the word for it? It's not De Morgan. Crap, I can see his face. Okay, I'm blanking on the guy's name. It'll come to me in a minute. Um, von Neumann. That's it. Neumann. Um, so von Neumann was a mathematician, sort of early pioneer in computing, and there were sort of two different approaches to architectures um, that were used back in the day. One was called the von Neumann architecture, where you have memory and your programs go into memory, and so does whatever other data that they need to work with. So they're all just sort of lumped into one big giant memory field. The other approach was the Harvard architecture. Um, and the Harvard architectures had separate memory for the program and for data, um, which um, which is kind of interesting. It meant that you had to address them separately, and so anyway, um, I guess to some extent you could argue that we still kind of use both, but really the von Neumann sort of architecture won out, and that's the one that we use. So hence we only have sort of one pile of memory rather than to some extent two. That's not 100% accurate, but it's close enough for government work. Okay, so the other thing we were talking about last time is that depending on how you structure your program and your use of your registers here, you've got 16 to work with. Maybe we could say really 15 because you need to leave register 0 kind of for special purposes for the jump commands. And for a really, really big complicated program, you're going to need more than 15 registers worth, right? So it may not be the case that you can store everything all at once. But that's okay because you can always store stuff out into memory and use sort of the tail end of memory here um, as stuff. So this is what makes this architecture and most architectures, they're called load and store architectures. So to do any data manipulation, you have to have a number or numbers in registers. Okay, so for example, to add two numbers, you had to first load those two numbers from memory into registers and then add them. That answer went into a register, and then you take the answer and put it back out into memory. So you're loading things from memory, you're storing things to memory. Um, and so pretty much all architectures kind of work this way with, little subtle details here and there. But um, yeah, And so the store part of it is what matters if you only have a few registers to work with. So, for example, last time we talked about the Intel, the x86 platform, which is what, most of you, if you're watching this, if you're watching it on a computer, it's got an x86 processor in it. It might be made by Intel, it might have been made by AMD, but it's the same architecture. If you're watching this on a tablet or a phone, then it's probably using an ARM architecture or a variant of those, which are very different architecturally. Yeah. So the Intel architecture only has basically 4 registers for general purpose use. It's got some others, but basically just 4. And so an Intel processor has to rely a lot more on memory of some sort. Um, because it doesn't have a lot of things on board the processor. Um, the ARM architecture, so the 64-bit ARM architecture, which is what's in pretty much every phone or tablet sold in the last 5 years or so, um, roughly, uh, it has basically 32 registers. And there's some uh, it's not like you have just 32 plain old registers. There's certain ones that have to get used for certain purposes and other ones that have to get used for other purposes. So in terms of how many you have, maybe say roughly it's 8 to 16 that you can sort of count on always being available. But again, you're going to run out of registers no matter what, and so eventually, and so you've got to just start storing stuff to and from memory. Um, okay, so let me just ask you guys, like Reese, Tyler, Filippo, kind of roughly where are you guys in terms of writing assembly for the various tasks? Um, and same thing with anybody else who's here in the either the so like Jimmy, Sam, um, who else do we have here? Teague. Um, how are we doing on the code? You may or may not be done with everybody thing already. All right, Filippo, you're desperate. What do you mean desperate? Um, yeah, it's challenging. Um, Especially checkpoint 3 and 4, right? Those are the tough ones. 1 and 2 shouldn't be too terrible, but yeah. Um, okay. All right. So let me stop here and make sure that see if there are any general questions that I can answer. Um, so um, about stuff, questions or problems you've run into, Filippo. Like, is there anything in specific that you've run into that's stumping you? Um, well, Patrick, um, and I feel like putting like a SpongeBob meme here on the screen or something. Where would you start if you haven't already? Well, definitely with task one, because task one is going to be similar to the positive negative program I wrote that's in the notes. It'll take a little bit of a modification of that. So in particular, because to test positive negative, you look at the far left bit, and to test for odd even, you look at the far right bit of a number. And so that's going to be the modification there, a little bit of detail. Um, all right, Reese, you're on number 2. Same thing with Tyler. Have you guys run into any issues with number 2 yet? And of course, my hint with number 2 is that because number 2 is basically to determine whether or not two numbers are equal, greater than one is greater than the other, or the other way around. So telling whether or not two numbers are equal is relatively easy. You can just put one of them in register 0 and the other one somewhere else, and then you just test whether or not those two registers are equal. Um, for not equal, or rather greater than or less than, um, then you know that A is greater than B if A minus B is greater than 0. And we know how to test whether or not a number is positive. And we also know how to test if, or how to do the subtraction, right? So we know how to do A minus B, and yeah. Now, Devin's suggestion here is actually really good, right? Is to actually work this stuff out on paper. Um, so yeah, exactly. So get out, a pad of paper and a pencil, and start writing assembly, and then over on the side, basically put your registers, and then kind of as you run through the program, so to speak. Um, then you can kind of change what value is in a register or erase it, and then put the updated value in the register. For um, sorry, for programs 1 and 2, you pretty much won't need that many registers, and so you can um, yeah. Um, and I mean, yeah, you don't have to do it on paper, as he's saying here. Um, then, but yeah, thinking things through on paper, and then putting stuff into the computer, or maybe typing out code in Atom, or you can just use Word or any other text editor. Actually, using Excel can actually be sort of handy for this, because then you can have different columns for the memory and whatnot. It really doesn't matter. Whatever is going to be helpful for you to get it done. But yeah, really thinking this stuff through on paper, literally step by step, right? So this is like literally as nitty gritty of programming as you can pretty much do. Um, and yeah, you could do it in tech, Reese. In fact, um, everything that I've written here um, is in tech. I wouldn't bother with tech, frankly. I would just put it in Atom, um, and there's no real need to tech it up. In particular, you if you and this will be useful actually for some of you guys moving on. Let me actually show you the tech source for this. Um, so when I did verbatim stuff, I used this environment called verbatim, and that makes the code look like it's actually code. And then up here in the pictures, that I'm loading in a package called Fancy VRB. Um, but that does makes the verbatim stuff. So if I want to put code, then I just put it in something like this, and then actually in one spot, let me find where I've done this. Oh, it looks like I just pasted it in. But one of the things you can do with the verbatim package is actually load in a separate file. So if you have a Python file or C or anything, you can just basically give it the file name, and it will load in the code from that file and then print it out and make it look like it does um, here. So like it doesn't have to put it in the box. That's sort of optional, but it makes it prints it and makes it look as if it's code. Um, yeah. So anyway, so I wouldn't bother with teching it, Reese. But this might be useful, for you and Mike in some other classes down the line, or in physics, where you've got both code and mathematical type setting that you need to have. So, of course, that's how I type pretty much anything that I give you guys. Is for the most part I do it in tech. Um, Occasionally I'll use Word if it's something quick and simple. So, um, okay. Um, yeah, the problem itself. So the problem that Mike is talking about is sort of the last version or the second version here, and in particular, um, this line right there at the very end, which is how do you do a shift left by a particular amount? Well, if you know the amount in advance, then you can just give a shift command. And as we discussed, I think last time, uh, let's say that you want to shift. Oh, I'm sorry. My face is covering the code. Yeah. There, that's better. We'll just put the code on the right. Um, yeah, sorry about that. Um, or I could open up OBS and just make it like giant face O McKinney. Um, we won't. Okay. All right. So anyway, the line I had highlighted was this one here. Um, answer. So this is to. So let's remind ourselves of the syntax here. The double less than symbol or double greater than means to shift number A by the shift amount. So if shift amount is say 17, then or so if this number shift were 17, then that would mean to take the bit pattern for num A and shift everything to the left 17 times. Um, and now, obviously, we can't shift more than 8 times on our processor, um, but yeah, that's what the syntax means. So, um, if you know in advance what this number is, so like let's say that you know for certain that you want to shift something to the left 3 times, then then to shift it left 3 times, that would be equivalent of shifting right 5 times. Okay, so how do we do that computation? Well, you do 8 minus whatever the desired left shift amount is, and then that gives you the right shift amount. Now, in terms of the processor, how do we do the subtraction? Well, we know what the encoding is for 8, right? That's just 0, 8 in hex. Um, and then how do we do subtraction? Well, that's when you do the flip the bits and the add 1 procedure. Um, it is worth noting, actually, that well, modern processors and even ones from the 70s had a single command that would do subtraction. Um, yeah, and so we don't have that, unfortunately. Okay, so Tyler's your question is: are you supposed to do Python assembly and machine code, or just the assembly and the machine code? The latter. So you guys are going to write assembly um, and machine code. Which let me go back here. In fact, let me just full screen this. Um, okay, because this is something that people um, do get confused about. So what's the difference between assembly and machine code? Okay, so here's this very, just for sake of example, this very early program that we wrote that all it did was added 2 numbers together. Okay, nothing special. So this, what I've highlighted there, that is assembly. Okay. Or really, the assembly is the stuff that says load and then the column right here. So load 101 and so on. This bit here is assembly. The stuff over to the right, so anything that occurs in a line after a semicolon is a comment. And so that means it doesn't actually do anything. It's just basically written in there for your use or anybody who's reading your code's use. But it gets ignored by the assembler when it's assembled in a machine code. Okay, so this is assembly, right? It's not quite as nice looking as Python or any other language, Scratch, whatever, right? Those are all high level languages. This is a low level language that is, but still somewhat human readable. Okay, then this is the actual assembly. I mean, the actual machine code. With here, I've got the down the left 0002, 0406, and 08. Those are the memory addresses where this stuff would be, and then the things to the right of it are the actual machine instructions, right? So this is machine code, this is assembly. And you guys are going to be producing both. Now, when you do this, there's a little bit of a back and forth, right? You first are going to write assembly, then you're going to turn it from assembly into machine code and test it on Joel's little emulator and make sure that everything works. So going back and forth between assembly and machine code is um, is relatively easy, right? Because each instruction in machine code corresponds exactly to one instruction of assembly. Um, but that's not the case with Python, right? So as we've seen, a line of Python or a line or two of Python could in fact be like 10 lines worth of assembly. Um, right. So yeah. So no, good question, Tyler. That you're just you are going to produce the assembly and the machine code. And the reason here is because I've already given you the Python, right? So the Python code is what's in the assignment file, and you of course can download those from they're hyperlinked and run them. Um, so the Python is basically just here what I use to basically write what the algorithm is that does this GCD problem. And then y'all's job basically is to take that and turn it into assembly and then hence machine code. Yeah, so you guys aren't going to be writing any Python here. Now, had the whole freaking coronavirus not happened, I would have actually had you guys writing some Python um, code, but for a different project. So one of the things that we obviously couldn't do remotely was the robotics programming stuff, because you kind of need robots to do that. Although there are some online tools and toys that we could have used. But anyway, point being, um, the robotics programming we were going to do in Python, and we would have spent a couple of weeks on that, but then the coronavirus happened. So thanks, coronavirus. Um, yeah, for ruining our fun. All right, so let's see. So good question, Tyler. Um, and Mike, I'll look at your code and see if we can sort out what the problem is um, there later. Um, Anybody else have any other questions? Are you going to have class for the next two class sessions? Um, Yeah, I've got a couple things that I wanted to show you guys, and in particular, I also wanted to have an opportunity to answer some questions. One thing that I wanted to start talking about a little bit is to show you guys on the circuit level how some of this stuff works. So how, for example, you can do an addition circuit, and for that, I'll post a link to this. Um, Oops. Um, Basically, what I want you guys to do is download this thing called Logisim Evolution, and I'll post a link to it um, on on Canvas so that you can download it. Um, but basically, what this thing will allow you to do is to make a basically um, to design simple circuits um, and or actually, complicated circuits for um, yeah. And so those of you guys who um, are going to go on with computer science, this is something that we would dive in a lot more in the machine architecture class. So Reese's question. Basically, I mean, I'm going to show you some stuff basically for funsies, but in terms of new content, I think we're basically done, and then the final project is it in terms of assignments. Um, so, um, yeah, so the stuff we do for funsies will basically just be for funsies. Um, and preview of coming attractions for those of you guys who are going to go on. Which actually bears me asking, how many of you guys are considering or registered rather for CS111 in the fall semester? Um, well, or who are considering, say, the CS major or minor. All right, so Patrick, you're registered. Anybody else? Let's see. Reese, Mike. Oh, you can't, Reese, because of a time conflict. Um, well, Teague, you're going to be graduating, bro, or at least you better. So, all right, Sam, good. Okay. Um, yeah, so the little bit of update on that. So, the fall semester of 111 and beyond. Sorry, there's one thing I don't like about this set of headphones, which is that if there's no audio for like half an hour or so, it turns itself off, but it doesn't include microphone input in that. So, yeah. Anyway, um, so Mike, you're taking it. But anyway, so 111 starting in the fall. 111 starting in the fall um, is um, will be using Python rather than Java. And there's some benefits to this. There's some drawbacks to it also. But um, yeah. So those of you guys who are going to continue on with stuff, you'll start with proper Python in the fall, and you'll obviously go into a lot more detail than what I've done here. Um, yeah, facepalm. So anyway, all right. So any other questions? Anything I can answer that's maybe kind of general? And Mike, I know you've got some specific questions, and I'm going to have to look over your code um, to figure that out. No, it's okay, Reese. I think it's kind of funny. My very first semester here, I was in Sparks having lunch one day, and some kid sat down and I was wearing a shirt and tie that day because I was getting photos done or something. And he looks at me, he's like, "So are you a sophomore, junior? What year are you? Because you're all dressed up. Do you have a presentation?" And um, um, so I was like, "No, actually, I'm a professor," and he was super embarrassed. So, Devin, actually, fun fact: the word you typed there, "roti," is actually the Klingon word for fish, um, which is hilarious. Um, so, yeah, um, that's sort of a joke that's built into Klingon. Um, so, yeah. Okay, any other questions I can answer other than what 1 plus 1 is, which is clearly fish, as we've discussed. Um, and if not, I'll end the stream and you guys can ask questions on Discord. Mike, in particular, your code question, I'll have to do it. Yeah, office hours later today. Yeah, pretty much. I've got um, I've got one phone call I need to make later this afternoon, and then obviously I'll need to eat dinner. But I'll be I'll be on Discord for most of the evening, so feel free to drop by and ask me questions there. We can do screen sharing and stuff so that we can talk through code issues. Um, yeah, so anyway, I would highly recommend that you guys be in the next day or two have gotten um, tasks one and two pretty much under control because those are the shorter ones. Task three is going to take a little bit more time, and then I think task four, don't even think about trying it until you've got task three completely working. Um, because it's sort of an evolution of task 3. Um, all right, well, we'll go ahead and quit for today. I'll post a link to Logisim here onto Canvas. It's a Java program, so you guys can download and run that. And there's a bunch of different versions of it, so I'll make sure we get to the right version. But this is a piece of software that we used relatively extensively my in the architecture course, because we can actually sort of start to design circuits um, that do the various little pieces of what a processor does. And eventually you can literally build an entire processor in Logisim and simulate the entire thing from start to finish, which is really freaking awesome. So anyway, all right. Well, I guess we'll quit the stream a little bit early today, and I'll give me a few minutes to get back on the laptop and out on the couch and head back to Discord. Um, what project, Devin? Oh, the processor? No, I still am working on it. I got kind of stuck, and then the semester ended, and then yeah, things happened. So, all right, so I'll go ahead and end the stream a little early today, and you guys can hit me up on Discord, and we can chat there. So I will see you guys on Discord and stop stream.